OCR Chemistry AS paper 2020. We're doing breadth in chemistry and we are doing section B. Okay, so this question is about atoms, isotopes and mass spectrometry. Complete the table to show the number of electrons that can fill the first 4 shells. Okay, so straight up you would have known that first shell holds 2 electrons, second 8, and third 18, and fourth 32, and you have come up about that because you would know that the s orbital contains 2 electrons, and the first shell is only the s orbital, so that's 2 electrons. The second shell holds the s and the p orbital, so that's 2 and 6, gives us 8. The third shell holds s, p, and d orbitals, so that's 2, 6, and 10, giving us 18. The fourth shell holds the s, p, d, and f orbital, and so that's 2, 6, 10, and 14, giving us a total of 32 electrons. Most elements contain atoms of different isotopes. State any differences and similarities between the atomic structures of isotopes of the same element. So that's just a definition of an isotope. So we know that the differences is a number of neutrons, but the similarities is they have the same number of protons and electrons. Okay, mass spectrometry can be used to identify the isotopes of chlorine. Part of the mass spectrum of chlorine is shown below. Calculate the relative atomic mass of chlorine. Give your answer to 2 decimal places. Okay, so what you do in these calculations is you have to take the relative abundance and times it by the mz and then add it to other peaks that you see. And so we know that the first relative abundance is 75.76, and that's for 35. So we do 75.76 times by 35 for chlorine, and then we're going to add other peaks that we see. So the other peak that we have is a percentage of 24.24, and that's for 37. So we do 24.27 times by 37. So afterwards we divide it by 100, and that would give us 34.48. And to check if your answer is correct or not, you have to go to the periodic table and to see if your answer matches or is very similar to the answer they have in the periodic table. So in the periodic table, we know that chlorine is 35.5, and so that is very close to the answer that we have here, and so 34.48 is the correct answer. The mass spectrum of chlorine, Cl2, also contains 3 molecular ions, so M+ peaks. One of the M+ peaks has an MZ value of 72. Suggest why an M+ peak at MZ 72 is observed and predict the MZ values of the other 2 M+ peaks. Okay, so chlorine is diatomic as they've given you here. So that's Cl2. And so that means we have 2 chlorines combining together, but chlorine exists as chlorine 35 and chlorine 37, and so that means they can have 3 possible combinations. So we can have Cl2 because we have Cl35 combining with Cl37, we can have Cl35 combining with Cl35, and we have Cl37 combining with Cl37. And if you do Cl35 plus Cl37, that would give us 72. If we have Cl35 and Cl35, that would give us 70. And Cl37 and Cl37 will give us 74. And that's the answer. So the peak at MZ72 is because we have a combination of Cl35 and Cl37. And the other 2 peaks that we'd get is at MZ70 and MZ74. And that's because of the other combinations that we can have. So this question is about compounds of bromine. Bromine reacts with phosphorus P4 to form phosphorus tribromide PbR3. Complete the electron configuration of a bromine atom. So first of all, we know that in order to fill in the shells, we have to find the number of electrons and they're equal to the number of protons. And bromine will have the number of protons is 35 in the periodic table, so that matches the number of electrons. And so we fill in the shells, but keep in mind that the 4s orbital shell fills before the 3d orbital. But this is the answer. Write the equation for the reaction of phosphorus with bromine. So they've given us that phosphorus here is P4, and bromine we know is Br2. And they've told us that they form phosphorus tribromide, which is giving us as PbR3, so we write it over here. But however, it's not balanced, and we've balanced it off if I just remove these. So this is the equation. But it's not balanced, and so we know phosphorus here is P4 and phosphorus here is 1, so we're going to add 4. So phosphorus is balanced, but the bromine is not. So we have 12 bromines over here where we have 2 over here. So we add 6, and now it's balanced. A compound of bromine is a solid at room temperature. The electroconductivity of the compound at different physical states is shown below, as shown in the table, sorry. So the physical state, if it's a solid, it will have poor electroconductivity, and if it's a liquid, it will have good electroconductivity. Name the type of lattice on the compound at room temperature and explain the different electroconductivities. Okay, so we know that this type of structure, where when it's a solid, it has poor electroconductivity, and liquid has good electroconductivity, is a giant ionic. And the explanation for this is because at a solid, the ions are fixed and they cannot move, whereas in a liquid, the ions can move and therefore can spread their charge. Okay, bromine reacts with fluorine to form compound A. Compound A is a liquid at room temperature and pressure but can easily be vaporized. When vaporized, 0.428 grams of A produces 76 centimeters cubed of gas at 1 times 10 to the power of 5 pascals at 100 degrees Celsius. Determine the molar mass and molecular formula of compound A. So molar mass just means mR. And automatically when we see we've got gas and we have pressure and we have temperature, then this equation coming to mind, PV equals nRT, and we can see that they want the MR, and we know we can get the MR by doing moles is equal to mass over MR, and we want the MR, and they've given us the mass, and we can use PV equals nRT to work out moles, and so we basically have the steps that we want to do in our head. So PV equals nRT, we're going to rearrange for moles, and so P should be in pascals, which we already have, so that's 1 times 10 to the power of 5. A volume should be meters cubed. They've given us here centimeters cubed, and so to convert from centimeters cubed to meters cubed, you have to divide by a million, because centimeters cubed to decimeters cubed is divided by 1,000. Then from decimeters cubed to meters cubed, divide by 1,000 again. So you can straight up divide by a million, or you can, if you like to, divide by 1,000 twice. And so that would give us 76 times 10 to the power of minus 6 meters cubed. And R is a constant, so it's just 8.314 and never changes. Temperature should be in kelvins, where they've given us in degrees Celsius. So to convert from degrees Celsius to kelvins, you add 273. So that's 100 degrees Celsius plus 273 gives us 373 Kelvin. So we plug that all into the formula, and that gives us 2.45 times 10 to the power of minus 3 moles. Okay, so now we have moles and we have mass. We can rearrange for MR. And so we're going to do 0.428 grams divided by 2.45 times 10 to the power minus 3 moles, and that gives us 174.6 grams per mole. That's just the units for MR. And so we've got the first bit of the answer, which is 174.6. Right. Now the molecular formula. Whenever they ask you to work on molecular formula using these type of questions, it's always a trial and error. So you're just going to have to keep on subtracting until you find the correct answer. But to make it easier, we know that it tells us bromine reacts with fluorine to form compound A. Therefore, compound A must contain only fluorine and bromine. So we're going to write the relative atomic mass of bromine and fluorine. So from the periodic table, 79.9, and we have 19. And so we start off with 174.6. For me, I find it easier if we subtract the biggest first. So I'm subtracting 1 bromine, so 79.9. That gives us 94.7. Okay, so that was my first step. So it gave us 1 bromine. And that would give us a remainder of 94.7. Now my second step, what I do is I see, well, how many fluorines can fit into 94.7. If it rounds up to a whole number, then that is the correct answer. If it doesn't, then I need to go back and subtract more bromines until I can find enough fluorines that will give me a whole number. So I'm dividing 19 because that's for fluorine, and that gave us 4.98. So 4.98 is 5 basically, it rounds up to 5. So that automatically tells me because I have a whole number, then that answer is correct. So bromine is Br 1 and 5F. F5. So that's the answer. So for example, say if I didn't get a whole number here and my ratio was very off, then I would go back and subtract another bromine and try this step again. And so that's what I like to do when it comes to trial and error. So, 23. This question is about barium hydroxide. Barium hydroxide is an alkali which releases hydroxide ions, OH- in aqueous solution. A barium hydroxide solution contains 3.89 grams of barium hydroxide in 100 centimeters cubed at 20 degrees Celsius. Calculate the concentration of hydroxide ions in moles per decimeters cubed of this solution at 20 degrees. Give your answer to the significant figures. Okay, so whenever you have long text like this and you've got different numbers thrown in there, it can be quite confusing for the students. So I have a rule for this, and it's always to write down the equation and fill in the concentration, moles, volumes, and in this case, because we have mass, then I put another table for mass and mol. So the first thing to do is write the equation. Majority of the time this is given, but in a question like this it's not given. But we can figure out, because it tells us that it's barium hydroxide and it's going to release hydroxide ions. So this is all happening in one solution. And so I know that this is it's just dissociating. And so I wrote barium and I wrote hydroxide, and it gave me barium hydroxide. You can also wrote this the other way around if you prefer, because it said releases. So you could have write barium hydroxide and it gets released to barium and hydroxide ions, right? I just prefer to write it like this. You could write it like this, no problem. And well, this is not balanced, so how do we balance it? Well, we've got 2 hydroxides and we've got 1 here. So now that's 2. So that's correct. But because technically this is minus, then I just like to put in the symbols, and barium is in group 2, so it will be 2+. But if you didn't know, that was in the periodic table anyway. It's just a metal in group 2. But the most important thing is just the balancing, because that will give us the correct ratio. And so we know that barium hydroxide and barium and hydroxide, it's a 1 to 1 to 2 ratio. Because I wrote it over here, I get 1 to 2 to 1. So the first thing you do is you write down the ratio. So you've got 1 barium and you've got 2 hydroxides, and that gives us barium hydroxide with a 1 ratio. Next thing, I write concentration, moles, and volume, and I've put in mass and ml, because usually you don't need to write this, but because if the question gives you mass, then you're going to have to basically use this equation where you do moles equals mass over ml. And so then I write a question mark on what they want me to find. So the whole aim of this question is to calculate the concentration of hydroxide ions in the solution. So I go to hydroxide ions and I put a question mark, so I know this is what I need to calculate. Then I plug in what I have, so what they've given me. So they've told me that the barium hydroxide solution contains this much mass. So I go to barium hydroxide and I write down the mass. So I've used this up, and it tells us in 100 centimeters cubed, so that's 100 here. However, this is all happening in one aqueous solution, right? So we've got barium hydroxide here, and it releases hydroxide ions. Therefore, the 100 centimeters cubed is also for the hydroxide ions. So I do 100 for hydroxide ions, and that means also 100 for barium, because these are all happening in one solution. So I've used this as well. And that's all I have. So whenever you have an equation, the only thing you can move around is the moles. The moles is what you can move around from side to side. Other things you can't. So if I see what I have, so I have this, and I have this, and therefore I have this and this, and I have the mass. So as we can see, if I have the mass and I have the MR, because I can calculate the MR for barium hydroxide, if I go into the periodic table, and if I add it together, it gives us 171.3. So I have the mass, I have the MR, and therefore that gives me the moles, right? And therefore I've plugged it in here because I've written in the table that this is the number of moles for barium hydroxide. Now, my whole aim is to calculate the concentration. So concentration is C and V, and I've got the moles now, so I'm taking it to the other side. However, this is a 1 to 2 ratio, therefore this number of moles is for 1 ratio. If I want it for 2 ratios, I'm going to have to double it. I'm going to times by 2, and that gives us 0.0454 moles. So now for the hydroxide ions, I have the moles. And the volume, yes, I have it. It's 100 centimeters cubed, so I'm going to convert to decimeters by dividing by 1,000. So I have the volume as well. I can now calculate the concentration. So 0.0454 divided by 0.1 gives us 0.454, and that's the concentration. So always write a table, add these on the side, and plug in what you have and what you need, and see how you can move around using moles. A student carries out a titration to determine the concentration of an aqueous solution of barium hydroxide. The student adds 25 centimeters cubed of barium hydroxide solution to a conical flask. The student titrates this solution by adding 0.16 moles per decimeters cubed of nitric acid from the burette. The equation is shown below. See, they're giving us the equation here. That happens the majority of the time. The student repeats the titration until concordant titers are obtained. The mean titer of 1.6 moles per centimeters cubed of nitric acid is 26.75 centimeters cubed. What is meant by concordant titers? Okay, so that's just the definition. So titers that are within 0.16 decimeters cubed of each other. That's the main thing to add in here. It's 0.1 decimeters cubed within each other. So calculate the concentration in moles per decimeter cubed of the barium hydroxide solution. So like I said, we do the equation, we write down the ratio, and we add moles, concentration, and volume. So the first thing we do is they want the concentration of barium hydroxide, and so I've put that as what I need to find the question mark. Then I plug in with what I have. So the ratio, so it's given to me over here. I didn't use the rest of the equation because we don't actually need it. We always need the first two bits whenever there's titration. So that's a 1:2 ratio, which I've written over here. I then plug in what I have using what they've given me. So the first thing here says 25 centimeters cubed of barium hydroxide solution. So I go to barium hydroxide and I write the volume as 25 centimeters cubed, but I know we're going to have to need it in decimeters cubed, so I automatically divide by 1000 to get 0.025 decimeters cubed. So I've used the first number they're giving me. Then it comes to 0.16 moles per centimeter cubed of nitric acid. So I go to the concentration and I go to nitric acid and I put 0.160. So I've used that as well. And then I scroll and okay, this is the same thing over here written again. And it tells me that the volume for nitric acid is going to be 26.75. So I go to the volume for nitric acid and I plug it in, divided by 1000 to get 0.02675. Okay, so I've plugged in everything they've given me and that's done. I now go to my little box that I've drew, and I'm going to start filling it in. So it's always C and V. So for nitric acid, they've given me the concentration, they've given me the volumes. I can use that to work out the number of moles. So I do 0.0267 and I'm going to multiply it by 0.16. And that gives me 4.28 times 10 to the power of minus 3. Okay, so I've written that here as my moles. And now I want to drag it to the other side because I have concentration, I have volume. If I can get the, I need the concentration, I have the volume. If I can get the moles, then I can work out the concentration. And I can see it's a 2:1 ratio. And so this is for 2 moles and I want 1 mole. So I divide it by 2 and that gives me 2.14 times 10 to the power of minus 3. So I've now got the moles, I've got the volume, I can rearrange for concentration. So I do 2.14 times 10 to the power of minus 3 divided by 0.025, that's my volume. And that gives me a concentration of 0.0856. And that's the answer. A student plans to prepare a solution of barium hydroxide from barium by 2 different reaction routes. Outline 2 reaction routes for preparing a solution of barium hydroxide from barium in the laboratory. Okay. Include 2 different equations. So you would have come across reactions of group 2 metals, and there's 2 ways we can form hydroxides. We can get the metal and we can react it with water straight away and we can get the hydroxide, or we can get the metal oxide and react it with the water to form the hydroxide. So there are 2 different reactions we come across, so I've written over here. So metal and water, or metal oxide plus water. So the first reaction would have barium and water. So barium plus water gives us barium hydroxide and hydrogen gas. So you would see that as bubbling. And I balanced it because I can see here I've got 4 hydrogens. And so H2O, I'll put 2 in front of the hydrogens to give us 4, and I've got a total of 2 oxygens, and so when I've added the 2 in front of the H2O, that would give me 2 oxygens. The other thing is I can use the oxide of group 2 metal plus water, so I can use barium hydroxide plus water. I've also written a formula how to make barium hydroxide, and so barium hydroxide will be just barium oxide. So barium plus oxygen gives us barium oxide, and we can see that I got 2 oxygens here. Well, I've got 1 oxygen here, so I balanced it by putting a 2. But now I've got 2 bariums, or I've got 1 barium here, so I add another 2, and that's how it's balanced. I then use the barium oxide and combine it with water to give us barium hydroxide, and that's already balanced. This question is about making ammonia and H3. Ammonia is manufactured by reacting nitrogen and hydrogen. So N2 plus 3H2 it gives us 2 NH3s. The standard enthalpy changes of combustion are given in the table below. So, sorry, given the table over here. Calculate the standard enthalpy change of formation for NH3. Okay, so the first thing I do is I write down the equations given us. I then, here you have to either, if it's for combustion, you write the oxides formed, and if it's for formation, then you write the elements. To be honest, you don't get any marks for writing this or not writing this, so I just drew a box. You know, you don't actually have to have it. You would have learned that if it's combustion, then arrows point down, whereas if it's formation, arrows point up. So I've told you that the calculate standard enthalpy change of formation, so we know arrows point up. However, the units the units that they've given, sorry, not the units, so the substance they've given you here are for combustion. Therefore, we use the arrows for combustion. It's never what they've written over here, but it's what they've given in here. Because they've written combustion, then your arrows should be for combustion and they point down. Next step is I plug in the values, so N2 is 180 and H2 is minus 286. However, we've got 3 lots of H2, so I times it by 3, giving us minus 678. And NH3, we have minus 293, which I have here, but I've got 2 lots of it, so I times by 2, giving us minus 586. So, second step is formation always goes, calculating this. Your next step is to draw this cycle, the arrow going around the cycle. So what we can see is the arrow points down. So for the reactants, it goes with the reactants, because it's split like this. So it goes down with the reactants, therefore the sign in front of your reactants, you don't change them because it goes with the arrow. And now when you go up from here, you're going against this arrow. So this sign has to change. And so if we write it down, then we have plus 180, that doesn't change. And we have minus 676, which doesn't change because remember both arrows are going down. So we keep that. And now when we're going back up, because we go like in a cycle, we're going against this arrow. So if it's minus 586, that's going to turn to a plus 586. And so I just write it down. I go plus 180 minus 678, and I'm adding 586. I basically just used the signs they've given us. And that gave us minus 92 kilojoules per mole. However, they want for NH3, and that was for 2 lots of NH3. Therefore, you have to divide your final answer by 2, giving us 46. Okay, the industrial manufacture of NH3 from N2 and H2 is carried out at an increased temperature and in the presence of a catalyst. Explain using the Boltzmann distributions why increasing temperature and using a catalyst both increase the rate of reaction. Right. So, I've drawn the Boltzmann distribution. So it's number of molecules against energy, and this is how it looks like. When we add a catalyst, it's going to decrease the activation energy, and so we write the activation energy as here, and with a catalyst we're going to lower activation energy, and so we're going to have more number of molecules that are able to react because they have sufficient energy. And so this is your first graph. When we use temperature, we're going to increase the temperature, and so what's going to happen is the Boltzmann distribution shifts more to the left hand side, and so more particles, so more molecules will have higher energy so they can react. And so this is what it looks like as your second graph. So this shifts and you have more particles. You can also write it down. So high temperature and a catalyst will result in more molecules colliding because we have more energy because they have more energy above the activation energy. And that's it. So this question is about unsaturated hydrocarbons. 2 reactions of propene are shown below. In the boxes, show the structures of the organic products of the reaction. Okay, so this is what we have, and it's going to undergo polymerization. So what you do here is you simply break the double bond, that's it. So you write the exact same thing, but you then extend these bonds from here to show that it's going to repeat. So the exact same thing, but you remove the double bond and you just increase these arrows, sometimes on its own, sometimes people add this. That's just to show it's one repeating unit. Now, combining with HBr, we get 2 different products because this is electrophilic addition, and we have HBr. The bromine can either attach here first, because you break the double bond, or it will attach here. So therefore we get two different products. We have a product where bromine is attaching second to the second carbon, or we have bromine attaching the first carbon. So you would write one with hydrogen here and bromine here, and the second will be bromine here and hydrogen here. Yeah, it just depends where bromine attaches, and therefore you get two different products because it's a double bond and it's breaking, so bromine can attach from the first carbon or on the second carbon, and that's it. Propene also reacts with bromine. Outline the mechanism for the reaction of propene with bromine. The structure of propene has been provided. Show curly arrows, relevant dipoles and products. Okay, so just electrophilic addition. So the bromine here, and as it approaches double bond, it gets partially charged because it causes a dipole. So we get a delta positive and a delta negative because it causes that shift in electrons. So the electrons get pushed closer to bromine, and so this bromine will be slightly negative, whereas this bromine will be slightly positive. And that causes the bromine, this bromine will break and attach to the first carbon. And now we have the second carbon that has no bond, and so it will be a positive charge. And we have bromine, because it took the electrons, will be Br minus with 2 electrons. Now, it's important that now bromine is going to go attack this carbon. It's important to show that the bromine, so the arrow goes from bromine and it hits the carbon, not the positive charge. So if I zoom in, and this is what we have, then you want to draw this, because this is correct. Some students would draw this, and be careful, it's not targeting the positive charge, it's targeting the carbon, so this can sometimes be seen as incorrect in the exam. And so that gives us the final answer of this.